Welcome! In this session, we'll explore LeetCode problem number 1031, maximum sum of two non-overlapping subarrays. This problem challenges us to find the maximum sum of two subarrays of given lengths while ensuring they don't overlap. It's a great opportunity to practice optimizing algorithms and working with prefix sums. Let's dive in. In this problem, we are tasked with finding the maximum sum of two non-overlapping subarrays from a given integer array nums. The lengths of these two subarrays are specified by the integers firstlen and secondlen. The key requirement is that the two subarrays must not overlap, meaning they cannot share any indices. Additionally, the order in which the subarrays appear in the array does not matter. For example, the subarray of length firstlen can be positioned either before or after the subarray of length secondlen. The input consists of the array nums and the lengths firstlen and secondlen, while the output is a single integer representing the maximum possible sum of these two subarrays. The array nums has a length between 1 and 1000, and its elements range between -10,000 and 10,000. The lengths firstlen and secondlen are both positive integers that fit within the bounds of nums. Let's now explore some concrete examples to better understand how this works. Consider the first example where nums is 0, 6, 5, 2, 2, 5, 1, 9, 4, firstlen is 1, and secondlen is 2. The goal is to find two non-overlapping subarrays with these lengths that yield the maximum sum. Here, an optimal solution is to select the subarray 9 with a length of 1, which corresponds to firstlen, and the subarray 6, 5 with a length of 2, which corresponds to secondlen. The sum of the elements in 9 is 9, and the sum of the elements in 6, 5 is 11. Adding these together gives a total sum of 20. Importantly, since the order of the subarrays does not matter, we could also choose 6, 5 first and 9 second, and the result would still be 20. Now, in the second example, the input is nums equals 3, 8, 1, 3, 2, 1, 8, 9, 0, with firstlen equal to 3 and secondlen equal to 2. An optimal solution here is to select the subarray 8, 9, 0 of length 3, which matches firstlen, and the subarray 8, 1 of length 2, which matches secondlen. The sum of 8, 9, 0 is 17, and the sum of 8, 1 is 12, giving a total of 29. This demonstrates how the algorithm identifies the best possible divisions of the array to maximize the sum, while ensuring that the subarrays remain non-overlapping. Finally, let's look at a third example where nums is 2, 1, 5, 6, 0, 9, 5, 0, 3, 8, firstlen is 4, and secondlen is 3. Here, one optimal solution is to select the subarray 5, 6, 0, 9 with a length of 4, corresponding to firstlen, and the subarray 3, 8 with a length of 3, corresponding to secondlen. The sum of 5, 6, 0, 9 is 20, and the sum of 3, 8 is 11, resulting in a total sum of 31. It's important to note that the problem includes constraints, such as ensuring the lengths of the subarrays are within the bounds of the array, and edge cases, such as handling arrays with all negative numbers or zeros. These constraints and edge cases guide the design of an efficient solution to handle all possible scenarios effectively. To tackle the problem of finding the maximum sum of two non-overlapping subarrays, we first considered a brute force approach. The intuition here is straightforward. For every possible starting position of the first subarray, we calculate its sum and then iterate over all valid starting positions of the second subarray, ensuring that there's no overlap between the two. For each pair of subarrays, we compute their combined sum and track the maximum value. While this method is simple to understand and implement, it has significant drawbacks. The key limitation is its time complexity, which is O(n squared). This arises because for each position of the first subarray, we perform a nested iteration over all valid positions for the second subarray. Additionally, the space complexity is O(1), since we don't require any extra storage. However, this quadratic time complexity makes the brute force approach impractical for larger input sizes, as the number of operations grows rapidly with the size of the array. The inefficiency of the brute force approach led us to consider an optimized solution, which combines the prefix sum technique with a sliding window mechanism. This method is designed to maximize efficiency while ensuring the subarrays remain non-overlapping. The key idea is to use a prefix sum array to precompute cumulative sums, allowing us to calculate the sum of any subarray in constant time. From there, we split the problem into two scenarios, one where the first subarray of length first len comes before the second subarray of length second len, and another where the order is reversed. For each scenario, we use a sliding window to dynamically maintain the maximum sum of the first subarray as we iterate through the array, which we then combine with the sum of the second subarray at each valid position. By considering both scenarios and tracking the global maximum sum, this approach ensures we capture the optimal solution efficiently. This optimized approach significantly improves upon the brute force method in terms of computational efficiency. The time complexity is reduced to O(n), as we only need a single pass through the array for each scenario, thanks to the use of prefix sums and sliding windows. The space complexity is O(n) due to the prefix sum array, though this could be reduced to O(1) by calculating range sums directly without storing the array. The advantages of this method are clear. It is highly efficient for large input sizes and eliminates the need for nested iterations. By reducing the complexity from O(n)² to O(n), we achieve a solution that is both faster and more scalable, making it a practical choice for this problem. An alternative approach to solving this problem involves dynamic programming. Here, we maintain two arrays, one that tracks the maximum sum of subarrays of length first len ending at or before each index, and another for subarrays of length second len. Using these pre-computed values, we can efficiently evaluate the maximum sum at each split point in the array. This method also achieves a time complexity of O(n), as we only need to traverse the array once, and a space complexity of O(n), due to the additional arrays. Compared to the sliding window approach, dynamic programming offers similar efficiency but requires extra storage for the DP arrays. While effective, it is slightly more complex to implement and lacks the simplicity of the sliding window method, which avoids maintaining additional arrays. After evaluating various approaches, the prefix sum with sliding window technique was chosen as the optimal strategy. This method balances simplicity, efficiency, and minimal space requirements, making it well suited for solving the problem. By splitting the task into two scenarios, one where the first subarray precedes the second and another where the order is reversed, we simplify the logic. The use of sliding windows allows us to dynamically maintain the maximum sum of the first subarray as we iterate, while prefix sums enable efficient range sum calculations. Together, these elements lead to an O(n) solution that is both scalable and easy to implement. Key insights include the importance of handling edge cases, such as ensuring the subarrays do not overlap, and recognizing that brute force, while intuitive, is impractical due to its quadratic complexity. Similarly, while dynamic programming is a viable alternative, its additional space overhead makes it less appealing than the sliding window approach. Overall, the chosen strategy strikes an excellent balance between clarity and performance, making it the most effective solution for this problem. The problem we're tackling here is to find the maximum sum of two non-overlapping subarrays of specified lengths, first len and second len. The key challenge is ensuring that the two subarrays do not overlap while maximizing their combined sum. Given the constraints, with arrays potentially as large as 10 to the power of 4 elements, a brute force approach would be inefficient. Instead, we use a combination of a prefix sum array and a sliding window technique to achieve an optimal solution in linear time. First, we start by constructing a prefix sum array, which allows us to compute the sum of any subarray in constant time. This is achieved by maintaining a running sum, where each element in the prefix sum array represents the cumulative sum of elements up to the previous index in the original array. Then, using a sliding window approach, we identify the maximum sum of the first subarray of length first len, iterating through the array while dynamically updating the maximum sum seen so far. This ensures that we have the best possible subarray of length first len at each position as we proceed further. Next, we employ a similar sliding window technique to compute the maximum sum of the second subarray of length second len. This process is done carefully to ensure that the two subarrays do not overlap. Specifically, we calculate the maximum possible sum of the second subarray both to the left and to the right of the first subarray. By iterating through the array in this manner, we ensure that we account for all valid configurations where the two subarrays are non-overlapping. Once we have the maximum sums for these two subarrays in each configuration, we combine the results to compute the total sum for every potential pairing of the two subarrays. Throughout this process, we keep track of the highest total sum encountered. To handle edge cases, we return 0 if the array is too small to contain both subarrays. Additionally, the use of prefix sums naturally accommodates negative numbers, ensuring that the algorithm remains robust even with such inputs. By combining these techniques, we achieve an efficient solution that avoids redundant computations. In terms of data structures, the prefix sum array plays a central role in enabling efficient subarray sum calculations. By storing cumulative sums, we can retrieve the sum of any subarray in constant time, which is essential for achieving the desired linear time complexity. To keep track of the best sums for the two subarrays, we use the variables maxFirst and maxSecond, which dynamically store the maximum sums encountered for subarrays of lengths firstlen and secondlen, respectively. This dynamic tracking eliminates the need for nested loops, further enhancing efficiency. The overall time complexity of this approach is O(n), as we make a single pass to compute the prefix sums and another pass for the sliding window computations. The space complexity is O(n), due to the storage required for the prefix sum array. The pseudocode for this algorithm first initializes the prefix sum array, then defines a helper function to compute the maximum sum of a subarray of a given length. Using this helper, we compute the maximum possible sums for both configurations where one subarray comes before the other. Finally, the solution returns the higher of the two possible combined sums, the sum of the first-len subarray followed by the second-len subarray, or the sum of the second-len subarray followed by the first-len subarray. This ensures that we account for both possible orderings of the two subarrays, guaranteeing that the optimal configuration is chosen. This concise logic leverages the prefix sum array and helper function to keep the implementation efficient and clear. By focusing on non-overlapping constraints and leveraging dynamic tracking of subarray sums, this approach efficiently solves the problem while adhering to the constraints. This solution computes the maximum sum of two non-overlapping subarrays using a sliding window and prefix sum approach. Here's the breakdown. 1. Prefix sum computation. A prefix sum array is built to compute subarray sums in O(1) time. Each element prefix, I, holds the sum of the first I elements of nums. 2. Sliding window logic. The function maxsum, L(m), is defined to calculate the maximum sum of two non-overlapping subarrays of lengths L and M. It iterates through the array, maintaining the maximum sum of the L-length subarray encountered so far, max L, and calculating the sum of the current M-length subarray. 3. Result update. For each position, the maximum sum of the two non-overlapping subarrays is updated by adding max L to the sum of the current M-length subarray. This ensures that the two subarrays do not overlap. For order handling, the method is called twice, once with first-len as L and second-len as M, and once with the order reversed. This accounts for both possible configurations of the subarrays. By leveraging prefix sums and sliding windows, the algorithm achieves O(n) time complexity. This ensures efficiency even for larger inputs, such as arrays with lengths up to 10 to the power of 4. Here, we begin by defining the main method maxsum_to_no_overlap, which calculates the maximum sum of two non-overlapping subarrays. The method uses a helper function, maxsum, to evaluate the maximum sum for two scenarios, one where the first subarray has a length of first-len and the second has a length of second-len, and another where their roles are reversed. This ensures we consider both possible configurations. Within the maxsum function, we first compute the prefix sums for the input array. The prefix sums help us efficiently calculate the sum of any subarray by subtracting the appropriate values. Next, we initialize two variables, max L, which tracks the maximum sum of an L-length subarray encountered so far, and result, which stores the overall maximum sum of the two subarrays. The core of the function involves iterating through the array starting from index L plus M, as this ensures we have enough elements to form both subarrays. At each step, we calculate the maximum sum of an L-length subarray that ends before the current M-length subarray. We then update the result with the sum of this L-length subarray and the current M-length subarray. Finally, we return the computed maximum result. The result variable ensures that we keep track of the best possible sum of the two non-overlapping subarrays identified during the iteration. The helper function completes its execution and passes the computed value back to the main method. By comparing the results of both configurations, the program guarantees that it returns the optimal solution. This structured approach, using prefix sums and iterative evaluation, ensures an efficient and clear implementation of the problem requirements. To solve this problem, we first compute the prefix sums of the array nums. The prefix sum array helps us calculate the sum of any subarray in constant time. We initialize prefix as an array of zeros with a length 1 greater than nums. Then, iterating through the elements of nums, we compute each prefix sum by adding the current number to the previous prefix value. For instance, the first value remains 0 because no elements are included yet. For the second value, we add nums, 1, to prefix 0, giving us a cumulative sum of 6. Continuing this process, we eventually construct the prefix array as 0, 0, 6, 11, 13, 15, 20, 21, 30, 34. Next, we calculate the maximum sum when the first subarray has length L equals 1 and the second subarray has length M equals 2. We initialize two variables, max L to track the maximum sum of the first subarray up to a given point, and result to store the overall maximum sum. Starting from index 3, which ensures both subarrays fit, we update max L to be the greater of its current value or the sum of the first subarray ending at IM. Then, we calculate the total sum by combining max L with the sum of the second subarray ending at I. Using this approach, we find that the maximum sum for this configuration is 20. Lastly, we reverse the roles of L and M and repeat the same steps to ensure we consider both possible configurations. The result remains 20 in this case, which we store for comparison later. For the second example, the input array is nums equals 3, 8, 1, 3, 2, 1, 8, 9, 0. With first len equals 3 and second len equals 2. Again, we start by calculating the prefix sum array, resulting in 0, 3, 11, 12, 15, 17, 18, 26, 35, 35. With the prefix sums ready, we proceed to calculate the maximum sum for the configuration where the first subarray has length L equals 3 and the second subarray has length M equals 2. Starting from index 5, we initialize max L to track the maximum sum of the first subarray up to that point. At each step, we update max L and calculate the total sum by combining it with the sum of the second subarray. For example, at index 5, max L becomes 11, and the total sum is 16. As we continue iterating, max L updates to 12, yielding a maximum total of 31 for this configuration. Reversing the roles of L and M, we repeat the same process with the first subarray having length M equals 2 and the second subarray having length L equals 3. Again, the result is 31. The overall maximum sum for this example is therefore 31, which we obtain by taking the maximum of the two results from the different configurations. In the third example, the input array is nums equals 103927, with first len equals 2 and second len equals 3. We begin by computing the prefix sums, resulting in 0, 1, 1, 4, 13, 15, 22. Next, we calculate the maximum sum for the configuration where the first subarray has length L equals 2 and the second subarray has length M equals 3. Starting from index 5, we calculate max L as the maximum sum of the first subarray up to that point. At index 5, max L becomes 1, and the total sum of the two subarrays is 18. Since there are no further indices to consider, the result for this configuration is 18. Reversing the roles of L and M, we repeat the same process with the first subarray having length M equals 3 and the second subarray having length L equals 2. The result remains 18. Therefore, the final output for this example is the maximum of the two results, which is 18. To analyze the time complexity of this solution, we start with the prefix sum calculation. Here, we iterate through the entire array once to compute the prefix sums, which takes n time. Next, within the maxsum function, we use a sliding window approach to calculate the sum of two non-overlapping subarrays. The loop in this function runs from L plus M to N plus 1, iterating over the array exactly once. Since the operations within each iteration, such as accessing the prefix array to compute subarray sums, take constant time, the total contribution of this loop is n. Additionally, the main function, maxsum2noOverlap, calls the maxsum function twice, once for each order of subarray lengths. Each of these calls takes n, so the total time complexity for both calls is n plus n, which simplifies to n. Overall, the solution achieves an optimal time complexity of n. Turning to space complexity, the main contributor is the prefix array, which is of size n plus 1, where n is the length of the input array nums. This requires n additional space. Beyond the prefix array, the algorithm uses a few auxiliary variables, such as max_l and result, which are scalar values and only occupy O1 space. Although the algorithm involves recursive calls to maxsum, the recursion depth is constant, as there are only 2 such calls, and no additional stack space is consumed. Therefore, the overall space complexity is dominated by the prefix array, resulting in O(n). When comparing this optimized solution to a brute force approach, the improvements in efficiency become clear. A naive solution would involve iterating over all possible pairs of subarrays of lengths first len and second len, checking for overlaps, and recalculating the sum of elements in each subarray. This would result in a time complexity of O(n cubed, in the worst case due to the nested iterations and redundant computations. By contrast, the optimized approach leverages the prefix sum technique to avoid recomputing subarray sums, while the sliding window mechanism limits the number of traversals to a constant factor. This results in a significantly reduced time complexity of O(n). Furthermore, when analyzing the best, average, and worst cases for the optimized solution, the time complexity remains O(n) across all scenarios. Regardless of the input size or distribution, the algorithm achieves linear growth in both time and space, making it highly efficient. To solidify our understanding, let's summarize the mathematical proof for the algorithm's big O complexity. For time complexity, the prefix sum computation runs in O(n), as it involves a single pass through the array. The sliding window loop in the maxsum function also iterates over the array once, contributing another O(n). Since the maxsum_to_no_overlap function calls maxsum twice, the total time complexity is 2 O(n), which simplifies to O(n). On the space complexity side, the prefix array requires O(n) space, while auxiliary variables such as max_l and result only use O1 space. Thus, the overall space complexity is O(n), dominated by the prefix array. This concise analysis confirms that the solution is both time and space efficient, scaling linearly with the size of the input. Common mistakes in this problem often revolve around misunderstanding the constraints or misapplying key techniques. One major issue is allowing the 2 subarrays, first len and second len, to overlap. This violates the problem's requirements and leads to incorrect sums. To fix this, we need to use prefix sums strategically, ensuring we calculate the maximum sums for non-overlapping ranges. Another common mistake involves miscalculating prefix sums or using them inefficiently. Since prefix sums are critical for reducing time complexity, any errors here could lead to wrong results or slower solutions. The solution is to compute the prefix sums once at the start and reuse them for efficient sum calculations. Additionally, many people focus only on one order of subarrays, such as first len before second len, but the maximum sum might occur when the order is reversed. To address this, we solve for both orders and return the maximum result, ensuring no potential solution is overlooked. Another common pitfall is relying on a brute force approach to check all possible subarray combinations. While this might seem straightforward, it has a time complexity of O(n cubed, which is impractical for larger inputs and will result in timeouts. Instead, we should use optimized approaches like sliding windows or dynamic programming to achieve an efficient O(n) solution. Edge cases with array bounds are also a frequent source of errors. For instance, if the combined lengths of the subarrays exceed the size of the array, it can lead to out-of-bounds errors or undefined behavior. The solution here is to carefully handle cases where the array is too small, ensuring that all indices remain valid and the constraints are respected. This problem is a strong test of your ability to optimize for non-overlapping intervals and efficiently compute sums, both of which are common patterns in interval-related problems. Mastery of prefix sums is particularly important, as it allows you to compute subarray sums efficiently, a skill that frequently comes up in interviews. Another key insight is the necessity of solving for both orders of subarrays, first len followed by second len and vice versa, to guarantee the optimal solution. This shows a thoughtful approach to considering all possibilities. Additionally, a solid understanding of edge cases, such as handling small arrays or equal subarray lengths, demonstrates attention to detail. Finally, being able to explain why optimized O(n) solutions are preferred over brute force, and how you manage memory and computational efficiency, is a great way to showcase your problem-solving skills. To deepen your understanding of related concepts, it's helpful to explore similar problems. For example, LeetCode 560, subarray sum equals k, also involves prefix sums and efficient subarray sum calculations. LeetCode 209, Minimum Size Subarray Sum, focuses on using a sliding window technique to tackle subarray sums. LeetCode 918, Maximum Sum Circular Subarray, introduces variations of maximum sum subarrays with the added complexity of circular arrays. Lastly, LeetCode 152, Maximum Product Subarray, shares similarities with maximum subarray problems but involves the additional challenge of handling products. Each of these problems can enhance your understanding of how to handle subarray-related challenges. There are alternative approaches to solving this problem, each with its own strengths and trade-offs. The sliding window approach can be used to calculate subarray sums efficiently, reducing complexity compared to brute force. However, it may be less intuitive than prefix sums for some. Dynamic programming is another option, where you maintain running maximums for subarray sums up to a certain index. While it offers similar performance to prefix sums, it can be harder to implement and understand. Finally, the divide and conquer method involves breaking the array into smaller parts and solving recursively. While this approach is conceptually elegant, it is less efficient, with a time complexity of n log n, making it less favorable than prefix sum or sliding window approaches in this case. Great job! We've explored an efficient approach to solving this challenging problem. Remember, prefix sums are a versatile tool for subarray-based problems, and tackling edge cases is key to robust solutions. If you enjoyed this, don't forget to like and subscribe for more walkthroughs. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!